Hello everyone, welcome to my presentation of our paper, Probabilistic Mission Planning Analysis for Multi-Agent Systems. My name is Rong, and this paper is written by me and my supervisors, Edward Inon, Christina Siciliano, and Christina Lundquist, and we are from Medellin University. First, I would like to introduce what are autonomous agents. These agents are systems that can move and perform different tasks in an environment. And most importantly, they can perceive and react to the event in the environment. So I give you two examples of these agents. One is the robots in autonomous warehouses where they can move and deliver different goods to shelves. And one is the autonomous vehicles in airports that can deliver the food or luggage to different airplanes. So as you can see, there are two crucial tasks to design this agent. One is path planning, which aims to generate a sequence of positions to visit. And one is task scheduling, which aims to generate a sequence of tasks to finish. And in this paper, we use an industrial use case called autonomous quarry. And this is provided by our industrial partner, Volvo Construction Equipment, Volvo CE. So in this quarry, we have two kinds of agents. One is autonomous wheel loader, one is autonomous truck. So the wheel loader simply digs stones and load the stones to the trucks. Then the trucks transport the stones to the primary crushers where the stones are crushed into fractions. And then the trucks move to the other end of the crusher and load the stones again and transfer them further to the secondary crusher. So of course, the agent needs to avoid all kinds of static obstacles and dynamic obstacles in the environment. And when their battery levels are low, they need to go to the charging stations to charge themselves. And based on the requirements from Volvo CE, we categorize the requirements of the agents into 4 categories. The first one is task assignment. So tasks must be assigned to the right milestones, like digging stones must be done at the stone piles, but not the other milestones. The execution order of the task also must be correct, like loading into the primary crushers must be done before loading to the secondary crushers. And milestone exclusion means some milestones contains a device that only allows one agent to operate at one time. So they are exclusive for agents. And timing requirement means that some tasks must be done within a prescribed time limit, like finish transporting 1,000 square meters of stones per day. So if you having that use case and the requirements in mind, let's have a look at how many things that we need to solve in this problem. If you separate the environment into 2 layers, just to see the problem clearly, in the upper layer, there's milestones where the tasks are supposed to be carried out, and there are some static obstacles where that the agent needs to avoid. So the product of solving the problem in the upper layer is the mission plan, which has the path plan and the task schedule. Okay, and since all the things in the layer are static, we can call it static layer. But once the agent starts to execute the mission plan, it might encounter some new unforeseen obstacles and some moving obstacles. So we need to know the concrete and continuous trajectory of the agent so that we know if it can avoid these new obstacles dynamically. So we call this layer, the lower layer, dynamic layer. And sometimes if the detour taken by the agents are too far away from the original mission plan, we need to replan, right? So we need the communication protocol in the middle to update the information of the map to the upper layer, the static layer, to do the replanning. And then we send the new plan to the lower layer, the dynamic layer, to see if the new plan is safe or not. And we propose this 2-layer framework in NFM 2019. But in this paper, we will be focusing on the static layer. But of course, we will also use some models in the dynamic layer. First, let's have a look at the path planning problem. Briefly speaking, we use Theta algorithm. Theta algorithm basically discretize the map into a Cartesian grid and calculates the shortest path between every two milestones. And you can see in picture 2, the paths are not stick to the edges or diagonals of the cells. They can be any angle. So this is the advantage of using Theta algorithm. Once we get the path, we need to know what is the order of visiting these milestones and how many times should they be visited, right? And what's more, if there are some pedestrians appearing, frequently in the map, we need to know when and how should the path be replanned, right? And these questions can be answered by task scheduling, which has its own difficulties. First, the execution time of tasks are uncertain. There are time intervals between the best case execution time and the worst case execution time. So our mission plan must consider any time point between this BCET and WCET. And also, if the agent, like agent 1 in this map, needs to go to one of the milestones, B and C, and all of them are occupied by other agents, the agent needs to wait, and the waiting time is uncertain, which makes the movement time uncertain too. So this is the difficulties. And also, the task scheduling is similar to the job shop problem, but it also considers uncertainties in the environment. And the problem is NP hard. And even if we fix the execution time of tasks and movement, the complexity of the problem can also grow very fast. Previously, we proposed a method called TAMAA, which uses the reachability verification in UPPAAL to generate mission plans for agents. But as you can see here, once the number of agents is 5 or more than 5, UPPAAL simply runs out of memory, never generates any result. So this is the problem of scalability. To solve this problem, we propose this method called MCRL, which combines model checking with reinforcement learning. But before I introduce this method, I just want you to know the models that are created by TAMAA, because these models are also used in the new method. So I need to build two kinds of models to model two actions of the agent. One is the movement, one is the task execution of the agent. So in TAMAA, I built the movement TA and task execution TA, and TA is short for timed automata. And these two TA are synchronized via a channel called Go. But I don't have time to go to the details of the model, so please check our paper if you are interested in the building of the model. And once we have the model, we verify them against some reachability properties in UPPAAL. And of course, if the properties are satisfied, we can obtain the execution traces of the model. And then we parse the traces into XML files, and we transfer the result XML files to the client side via a network, where we have a GUI called MMT. It is developed by our colleagues from the university, and we can show the result mission plans in this GUI. And in the first step, TAMAA uses exhaustive state space exploration, which causes the notorious state space explosion problem. Okay, this figure simply shows the process of reachability verification. So the model checker needs to exhaustively explore the state space of the model and also stores the states until it reaches the goal state, where it reaches all the states and figured, okay, there's no state can satisfy the reachability property. So once the state space of the model is too big, the model checker simply exhausts all its physical memory. So that's why we encountered the auto memory error in UPPAAL when we use TAMAA. In the new method, we use reinforcement learning and random simulation to conquer this problem. So this picture shows the overall workflow of MCRL. In the beginning, we gather data via simulation. And after the simulation is done, we can sample some traces from the state space And then we input these traces to the learning module, which is the Q-learning, for example, in this case. And Q-learning produce Q-table, which is used in the final step to reform the model so that the new agent model can be controlled by the Q-table. I'm going to introduce these 3 steps in details, but before that, I want you to know that Q-learning is a classic reinforcement learning algorithm, and it uses Bellman optimality equation here, and it produces Q-tables like this one. This is a Q-table for a robot moving in an environment. So the states of the Q-table, for example, in this one, is the locations of the agent or the robot. And the action in the Q-table is the available actions for the robot, like moving left, right, moving up and down. So Q-learning simply calculates and accumulates the rewards that the robot can get by taking an action at a certain state. After the Q-table is produced, we can see, okay, at the station, at the location MT1, taking the action of moving down has the highest reward. So this is the best action at the current state. Then the robot, of course, take this one. So in this way, the Q-table can serve as the mission plan that we want the agent to use. Okay, now let's have a look at the first step, data gathering. To gather data, we randomly simulate instead of exhaustively explore the state space, because this one does not have the out of memory error. But to do that, we need to use UPPAAL SMC. SMC is short for Statistical Model Checking, and this tool provides a query in the yellow box. This query simply simulates the model for T time units and R rounds, and prints out the information in the curly brackets. Once the traces can satisfy the predict following this query. So briefly speaking, we can say these traces are sampled from the simulation. And of course, to do the random simulation, we need to assign some probability distributions to the model. And we use the default one, like the time-bounded delays use in a uniform probability distribution in UPPAAL SMC, which means the execution time of tasks uniformly distributed in the time interval of BCET and WCET. And another change of the model is to change the channels to broadcast in UPPAAL SMC. And also we add 2 functions on these 2 models so that we can record the current Q state, Q action, Q values into the Q table of the model. And the Q table in UPPAAL is simply an array of data structures. The first structure is the Q state, and second structure is the Q action, and the Q value is stored as an integer. So once we have the models modified and we have the Q table introduced, now we can have a look at the detailed process of the method. In the beginning, we rerun the model in UPPAAL SMC in command line. So from command line, we can produce the sampled traces into a txt file, and then we put this txt file in a Java program, which also implements the Q-learning. And then the Java program simply populates the Q table and prints out the C code array of the Q table. And then we input this code into the model to reform the model, so that now the agent model is equipped with the Q table. Now the problem is, who should do the searching and returning work? Like search the Q table, find the action with the highest reward, and return the action to the TA models of the agent so that they know which action to take. Who should do the work? We create a new model called Conductor. This model simply searches the Q table and return the action with the highest reward. And then the model sends commands to the movement TA or the task execution TA via different channels. So the specific TA is synchronized with the conductor TA via the specific channel, and other TA have to wait. In this way, the conductor TA actually controls the behavior of other TA based on the information of the Q table. Okay. And this is what we call model reforming. Now the model is under the control of the Q table. Now, if we look back to the requirement, we designed 4 different properties or queries in UPPAAL to check the probability of satisfaction of the requirements. And I don't have time to go to the details, but I can tell you that all the requirements are satisfied by the mission plan that are synthesized by MCRL in our use case. And the probability are all above 99.9%. And now I just want to introduce 2 interesting analyses that we did via statistical model checking in this example. So if you remember, the agents might need to wait at some milestones because they are occupied by other agents, right? So now we want to know which milestone in the map has the longest waiting time and the highest probability of waiting. So we designed this query to estimate the probability of waiting and the waiting time. And the result shows that, okay, milestone D has the highest probability of waiting, and the waiting time can be longer than 1 time unit and less than 2 time unit. So maybe based on this result, designer of this query knows the bottleneck in the map, which is secondary crusher. So he or she can maybe increase the number of the secondary crusher to make the mission plan more efficient. And second analysis that we did is about the traveling time estimation and replanning. So if agent 1 needs to go to milestone D, the best way, of course, is via milestone C because it is closer. But if there's some pedestrian appearing frequently in milestone C, maybe going via milestone B is the better way, right? But we don't know that. So we want to see if the algorithm can actually choose a better way based on different scenarios. So we reused the hybrid automata in the dynamic layer that we introduced earlier to get the concrete and continuous trajectory of the agent, and we can estimate the traveling time of the agent. And also we have a model called pedestrian generator. It basically generates pedestrians dynamically during the verification time or simulation time. And here's the exponential rate. The higher the rate is, the more likely the pedestrians can appear. And we designed 2 scenarios. In the first scenario, the exponential rate is lower. So the maximum number of pedestrians that appear at the same time is 2. And the existing time of them is shorter than the second one, because the second one has a higher exponential rate. So the number of the pedestrians are up to 6, and the existing time are longer. So we basically verify those hybrid models against this property. It checks the time of reaching the milestone C within X time unit. And based on the result of this verification, we can have these 2 models. The first one, in the first one, going to milestone C fast is much likely than going to milestone C slowly, because of course the pedestrians are fewer. But in the second case, going fast is much less likely than going slowly because the pedestrians are more. So based on these models, we synthesized the mission plan by using MCRL, and then we verified this property against the mission plan that we synthesized. So this property means the agent can always go to milestone D via milestone C, but not via milestone D. And we want to check the probability of this query. So the probability of this query in the first case is much higher than the probability in the second case, which means In the first case, it's more likely to go via milestone C, and in the second case, it's more likely to go via milestone B. So this result shows the capability of our methods to do the replanning in different scenarios. In conclusion, we propose MCRL to synthesize mission plans for multiple autonomous agents working in an environment containing uncertainties. And the number of agents that MCRL can handle is more than that of the graph search-based method like TAMAA. Of course, I didn't mention that in the presentation because this is reported in another paper of this study. But this is very important, so I just want to include it in this conclusion. And also, we can use statistical analysis of the synthesized on the synthesized mission plans to show the quality and the bottleneck and the ability of replanning of the mission plans. For future work, we want to integrate our method into the tool called Statistical, which is designed to synthesize strategies for timed games. And also, if the mission plans are too big, we also want to compress it so that it can be used in some embedded systems that have limited memory space. And actually, these two works have been done because this paper are supposed to be published last year. So we welcome the audience to check our new papers that will be published soon. But also, we have another interesting point. We want to increase the learning efficiency by using the model checking results. So for example, if some synthesized mission plans cannot satisfy the requirements that we wanted to satisfy, then we can use the counter examples returned by the model checker to kind of repair this mission plans. So the learning efficiency can become even higher. So this is my presentation of our study, and welcome for any questions. Thank you.